Hello students. So, in your previous class we started with Green's theorem in vector calculus. So, we saw that if you have two functions say m and n which has continuous partial derivatives with respect to x and y, then in that case you can be able to write this identity del n del x minus del m del y dx dy is equals to line integral m dx plus n dy, and you take the integration this line integral in such a way that the region R which is being enclosed by the curve C is always on the left hand side. So, that means in a way you are walking in anti-clockwise direction. All right. So, that was the statement of Green's theorem. Today we will verify few Green's theorem with some examples. The thing is, why do we have to study these theorems like Green's theorem, Gauss theorem or Stokes theorem? So, you can see that on the left hand side you have a surface integral, but on the right hand side you have a line integral. So, sometimes it is not easy to evaluate this line integral, and if your m and n they have continuous partial derivatives, then you can basically evaluate just take their partial derivatives and then you can evaluate their surface integral, and most of the time it becomes a very simple expression, or you have a let us say surface integral and it has a complicated region and other things. So, what you do, you basically identify your m and n and then you evaluate the line integral. So, it is a very handy tool to convert a surface integral into a line integral or a line integral into a surface integral, and sometime and most of the time it actually make our life easier to evaluate either one of them when the respective integrals are in surface or line and they are complicated in a way. So, just to do this conversion, sometimes we may be able to evaluate the integral easily, but right now we will just verify this theorem. So, let us see how we can do that. So, in order to verify, let me start with this example. So, verify Green's theorem in the plane for integral over the curve C x y plus y square dx plus x square dy, where C is the closed curve of the region bounded by y is equals to x and x square equals to y. All right. So, first of all in order to verify the Green's theorem, first of all we have to identify what is our m and what is our n. So, let us look at the statement. So, in the statement it says that you have a circulation or let us say line integral m dx plus n dy. So, here you have dx and then this thing and then you have dy and then this thing. So, that means this must be our m and this must be our n. So, by Green's theorem in the plane, what is the plane? So, we have x y. So, this is our line y equals to x and then we have a parabola x square equals to y. So, this must be our parabola. All right. So, we have to walk in such a way that the region R must be on the left hand side. So, that means we are walking in the anti-clockwise direction, and then this point of intersection let us say P can be obtained. So, they basically intersect at 2 points, first at origin and then the second one at P. So, by Green's theorem in plane, this we have to verify del n del x minus del m del y dx dy is equals to line integral C m dx plus n dy, where n is x square n x y basically, and m x y is x y plus y square, right. So, these are our m and n. Now, the curves y is equals to x and x square equals to y intersect at. So, we can solve these equations, these two equations, to obtain the point of intersection. So, if you solve them, then basically what we have to do is substitute x square equals y equals to x. So, this will be minus x. So, the two possible points are 0 and 1, and so y is also 0 and 1. Therefore, they intersect at 0 0 and 1 1. So, we just solve these two equations and we will be able to obtain these the point of intersection as 0 0 and 1 1. All right. So, we have these 2 points of intersection. Now, in order to verify the Green's theorem, we first calculate del n del x and del m del y. All right. So, del n del x would be del x of x square. So, this is basically 2 x, and del m del y would be del y of x y plus y square. So, this will be x plus 2 y. All right. Now, we will calculate the surface integral. So, del n del x, which is 2 x minus del m del y. Let me write the expression. So, we have del n del x minus del m del y dx dy. So, surface integral over the region R, del n del x would be 2 x minus 2 y, and then this is dx dy. So, this will be ultimately integral over R x minus 2 y dx dy, right. And now, in the region R, our x is varying from 0 to 1. If we see, x is varying from 0 to 1 and y is varying from x square to x, right. So, y is varying from x square to x is varying from 0 to 1. So, let me write those limits here. So, x is varying from 0 to 1 and y is varying from x square to x minus 2 y dx dy. So, we first integrate with respect to y. So, this will be x running from 0 to 1, then integral y running from x square to x minus 2 y dy and then dx. So, we integrate with respect to y first, substitute the limit, and then we integrate with respect to x. So, ultimately we will obtain, after integrating with respect to y and putting the values, x to the power 4 minus x cube dx. So, this will be x to the power 5 by 5 minus x to the power 4 by 4, and x will be running from 0 to 1. So, this will be basically 1 by 20 minus 1 by 20. Now, that is the surface integral. Now, we will evaluate the line integral to match the values, whether they are same or not. So, and for the circulation part, we see that of course, it is a closed curve, but it is a piecewise smooth curve actually. So, it is continuous from here to here and then here to here. So, we actually evaluate the line integral along these two paths. So, first we will evaluate along this path and then we will evaluate along this path. So, we did an example like this. So, if we go back, so this is our C, m is basically x y plus y square. So, x y plus y square dx and n is x square dy. So, along we can let us write C 1 x y plus y square dx plus x square dy, and then we have another integral C 2 x y over C 2 x y y square dx plus x square dy. So, what do we have is basically is I am calling this one as C 1 and this one as C 2. So, the part of the parabola is considered as to be C 1 and the part of the straight line is considered as to be C 2. Now, along C 1 basically, now along C 1 we have y is equals to x square and therefore, dy is equals to 2x dx. So, I will substitute dy is equals to 2x dx here, and x will vary from 0 to 1, and similarly along this line we have y is equals to, and along C2 we have y is equals to x. So, dy is equals to dx. So, we substitute y is equals to x and dy is equals to dx. So, let us call it as IC. So, IC is basically integral over C1, that means x is running from 0 to 1, x y is basically x square plus x to the power 4 dx plus x square 2 x to the power 3 dx plus integral x running from 0 to 1 along C2, y is x. So, this is basically x square plus x square dx plus x square dy. So, dy is basically dx. Now, we have to evaluate this line, this integral where the limit is from 0 to 1. Let me put everything in the bigger bracket. So, this is our given integral, and if you evaluate this whole thing, then it will be actually you will obtain as minus 1 by 20. So, this is not very complicated to obtain. So, of course, there will be a minus sign here, because I forgot to tell you, because we are going in the reverse direction. So, if we are going in the reverse direction, that means we are going from 1 to 0. So, if we are going from 1 to 0, then I want to reverse the direction, I want to go from 0 to 1. So, I have to put a minus sign here. So, this is an obvious thing that we have to remember, and keeping a minus sign here, because initially it was supposed to be 1 to 0. So, now we are doing 0 to 1. So, a minus sign, and then you evaluate, and then basically obtain minus 1 by 20. So, you see, this is how we verify the Green's theorem. So, it will be slightly lengthy, because all these theorems. So, Green's theorem, Stokes theorem or Gauss theorem, if you want to verify, then it will be lengthy, because you have to check both sides of the identity. So, here in this case we had to guess what is our m and n, and from there we had to calculate del n del x del m del y, and then substitute here and simplify the surface integral. Similarly, for the line integral, I had to calculate the line integral along two different paths and substitute here, and just see whether the two sides are equal or not. So, since the both sides are equal, that means that actually the Green's theorem hold true in this case. All right. So, this was an interesting example where you verify the Green's theorem. Let us consider another example where we can use the Green's theorem to simplify a given integral which is slightly complicated. So, example 2, evaluate by Green's theorem line integral over C x square minus cos hyperbolic y dx plus y plus sin x dy, where C is the rectangle with vertices 0 0, pi 0, pi 1 and 0 1, right. So, we basically have a region R. So, let me draw this region R, x, y. So, this is our rectangle. So, we have vertices 0 0, pi 0, which is say A, then B is pi 1, and then B is pi 1, and then this one is 0 1. All right. So, this is our region R, this is the curve C, along which we have to calculate this line integral. So, by Green's theorem we know that. Now, we will see first whether the Green's theorem is applicable or not. So, first of all, we have x square minus cos hyperbolic y, which is obviously differentiable and have continuous first order partial derivative, and then we have y plus sin x, which is again having continuous partial derivatives. So, that means these are our m and n, and they both behave nicely. So, by Green's theorem we have to write, or we have to when we use. So, we when we use Green's theorem, so this will be del n del x minus del m del y dx dy integral c m dx plus n dy. So, that means, since our m and n have a continuous first order partial derivatives, I can use Green's theorem, and therefore, this line integral can be converted into a surface integral, right. So, if I convert this line integral into a surface integral, then our n is n x y is basically y plus sin x. So, from here del n del x would be cos x, and our m x y is x square minus cos hyperbolic y. So, if we differentiate, then del m del y would be minus of sin hyperbolic y, right. All right. So, then we substitute in this surface integral, let us say I r is equals to surface integral over r, del n del x is cos x minus plus sin hyperbolic y dy dx, and then dx dy. So, then r for the region r, x is varying from 0 to pi and y is varying from 0 to 1, and then we have cos x plus sin hyperbolic y. So, since we have we do not have any product of x and y or something. So, that means, here we do not have a function of y, or here we do not have a function of x. So, it is fairly easy to integrate, because then we separate the terms, and once we separate the terms, then this will be basically integral x running from 0 to pi. We first integrated with respect to y. So, this will be y cos x plus cos hyperbolic y is from 0 to 1 dx. So, this will reduce to integral x running from 0 to pi cos x plus cos hyperbolic 1 minus 1, because cos hyperbolic 0 is 1. So, cos hyperbolic 1 minus 1, and when we integrate, then this will be sin x cos hyperbolic 1 minus x 0 to pi. So, this will be sin pi is 0. So, pi times cos hyperbolic 1 minus 1. So, you see, initially we had a very complicated line integral to evaluate, but we just took help of Green's theorem, which says that you can be able to use this identity only when m and n have continuous first order partial derivatives with respect to y and x, I believe. And since our functions are behaving nicely, I just calculated the partial derivatives and put it on the left hand side of this formula, and that gave us this nice result. All right. So, this is one such situation where we can use that theorem and obtain the required surface the required result. Similarly, we can have solve another example. So, let us consider evaluate this example, evaluate by Green's theorem. So, here it says specifically Green's theorem cos hyperbolic cos x sin y minus x y dx plus sin x cos y dy, where C is the circle, x square plus y square equals to 1. All right. So, here again we are given a very complicated expression to evaluate, and obviously, when you are told that you have to use Green's theorem, then you really do not have any way out. So, we see how we can use the Green's theorem. So, first of all, we have cos x sin y x y sin x cos y. So, they are all very nicely behaving functions. So, obviously, they have continuous partial derivatives. So, we do not have to worry about that. So, then we can write here m x y is sin x cos y. So, what will be our del m del y? Del m del y will be minus of sin x cos y, right, and cos x sin y sin x cos y. So, if I differentiate, so this will be minus of sin x minus of sin y, okay, sin y. So, this is sin y, and n x y is cos x sin y minus x y. So, this will be del n del x, and del n del x would be minus of sin x cos sin y minus of y. So, therefore, by Green's theorem, we have over region R del n del x minus del m del y dx dy is equals to line integral m dx plus n dy. So, del n del x is minus of sin x sin y minus y, and this one is plus sin x sin y. So, you see we will basically obtain a very simple expression to solve. So, instead of working with this complicated one, we will obtain a very simple expression to work with. So, let me write IR. IR is over R del n del x minus del m del y dx dy. So, what is our del n del x? So, del n del x is minus of sin x sin y minus y minus of sin x sin y minus y and minus del m del y minus minus plus. So, this will be plus sin x sin y. So, they both will get cancelled dx dy, and then we will basically obtain over region R minus of y dx dy, right. So, now for this circle R, our x will vary from 0 to, so the equation of this circle is 1. So, our x will vary from 0 to 1 and y will vary from 0 to minus of 1 minus x square to plus 1 minus x square y dx dy, right, because our that is the range for the y, and the range for the x is so the range for the x is 0 to 1, or what we can do. So, here you can integrate, and then we basically obtain here so del n del x. So, this is my m. Oh, sorry. So, this is our m and this is our n. So, that m. So, this is my m. So, del m del y is cos x sin y. So, this is cos x, excuse me. So, this is cos x. So, this will be I think I took the wrong m actually. So, this will be cos x cos y minus of x, and this is my n. Yeah, this is my n. So, this will be del n del x. So, this is del n del x, and del n del x is cos x cos y. Yes. So, this will be cos x cos y. So, this will be cos x cos y. So, if now if I substitute, then this will be minus minus and then plus. Yes. So, this is basically so ultimately here we will obtain cos x cos y. So, we will obtain cos x cos y cos x cos y plus x minus of cos x cos y. So, ultimately we will obtain here is x dy dx, right. So, we will obtain basically x dy dx. So, either we can have x 0 to 1 and y running from minus 1 minus square root of 1 minus x square to plus 1 minus x square x dx dy, or we can substitute x equals to r cos theta and y is equals to r sin theta. So, then in that case this surface integral I r would reduce to integral over the region R. Our r will vary from 0 to 1 and theta will vary from 0 to 2 pi. X will be r cos theta and dx dy will be r dr d theta, and then basically this will be if we integrate cos theta, then this will reduce to r running from 0 to 1 r square dr, and then we will integrate 0 to 2 pi cos theta d theta. So, if I integrate cos theta, then it will be sin theta, and sin theta at theta equals to 2 pi, it will be basically 0, because at theta equals to 2 pi and theta equals to 0, this whole thing is 0. So, ultimately the value of the integral is 0. Yeah. So, here you can see that for this given vector for this given expression here, where we had to calculate the line integral for this curve C, yeah, I guess the function incorrectly. So, this is my m and this is our n. So, we have to calculate del n del x, which is cos x cos y, and then here we have to calculate del m del y, which is cos x cos y minus x. So, we substitute the whole thing in this expression on the left hand side, and then we do some calculations, and either we can proceed in this way, or we can proceed in this way. It is up to us, and we just substitute x equals to r cos theta, y equals to r sin theta, and the ultimate answer is 0. So, looking at this integral, it would not have been easy to guess the limit that to guess the value of the integral, not the limit, to the value of the integral, that it will be 0, but it is just that taking help of Green's theorem, we can be able to show that the value of the integral is 0 by doing some simple partial derivative. So, you got the idea that what we have to do actually. There might be some errors here and there while doing the calculation. I hope you would understand. But yeah, the message is that whenever you have a complicated line integral given to you, and if your m and n seems to be having continuous partial derivatives, then try to use Green's theorem, and there is a strong possibility if you use the Green's theorem, then the whole integral will reduce to a very simpler one, and you just like in this case or in the previous case, you just do some simple known formula or known calculation to obtain the value. So, today we tried to learn about Green's theorem, and we also saw its how to say efficiency, that how you can use it and how it makes our life easier while calculating the integral, surface integral or line integral. So, I will stop here for today now, and in our next class we will start with the Gauss divergence theorem. So, I thank you for your attention.